This week we'll be having a math review. All of these things you should have seen before, but they're very important to be successful in physics, so we're going to go over them again. There are a lot of things that we're going to cover in a short amount of time, so it's going to be rather intense, kind of like boot camp. The first topic in Math Boot Camp is going to be scientific notation. Scientific notation is a way to quickly write out long numbers. Because, in all honesty, physicists are kind of lazy. So we like to find shortcuts. In order to convert, we follow these steps. First, you move the decimal so that only one digit, or a number other than 0, is to the left of the decimal. You count the number of spaces that the decimal moved. Okay. Now you will write the number without the extra zeros and add times 10 to the power of whatever number of spaces you counted. If you move to the left, the exponent is positive. But if you move the decimal to the right, then the exponent will be negative. These rules are opposite if you're going from scientific notation to what we call standard notation, or a normal way of writing numbers. Let's try a couple examples to make sure you remember this. Okay. Example number 1 says express 8,275,000 meters in scientific notation. In this example, it is understood that the decimal starts at the end of the number. So I'm going to rewrite the number so that I have room. Okay. So the decimal starts here. Our first step is to move it so that it has just one number before the decimal. And now we need to count how many spaces we move the decimal. 1, 2, 3, 4, 5, 6. So the proper way to write this number in scientific notation is 8.275 times 10 to the 6th meters. Moving on to example number 2. This example says express 0.00287 kilograms in scientific notation. So again, I'm going to rewrite the number so I have plenty of room to work. Okay. And my first step is to move the decimal so that there's one number that's not 0 before the decimal. So that means the decimal needs to go between the 2 and the 8. Okay. I had to move the decimal 1, 2, 3 spaces. Because I had to move the decimal to the right, that means my exponent is going to be negative. Therefore, the proper way to write this is 2.87 times 10 to the negative third. Now let's look at a third example. This says express 8.675 times 10 to the 5th in standard notation, or the way we would normally write it. So first, I rewrote the problem, and then I wrote the numbers given without the decimal. Because we're working backwards and going from scientific notation to standard notation, now a positive number indicates that I move to the right. So I'm going to start where the decimal was and count 5 spaces to the right. Right here we have 2 spots where there's nothing there. That means I need to insert a 0 as a placeholder. So now we have 867,500 as our new number. Now the fourth and final example. Here it says express 1.12 times 10 to the negative 7th in standard notation. Again, because I'm going from scientific notation to standard notation, our rules are opposite. This time a negative number indicates that I need to go to the left when I move the decimal. The decimal started between the ones, so we're going to move it 1, 2, 3, 4, 5, 6, 7 spaces. Again, all these empty spaces must be filled with zeros. So the correct way to write this in standard notation is 0.00000000112. As you can see, this is kind of a long, drawn out number, and this is the main reason we use scientific notation, to avoid miscounting our zeros and to save time. On many occasions, we will have to do calculations with numbers in scientific notation. So let's practice doing some calculations with the exponents. When we have exponents, the first thing we do is we're going to do the operation in two parts. The front numbers as 1, and the exponents as something else. And the exponents have their own set of rules. And depending on what the exponents look like, the kind of mathematical operation we're doing depends on which rule we're going to use. This is a table including all of the laws of exponents as they would be written in your math book, as well as an example of what they may look like. We will not need all of these rules, but I am giving them to you as a reference. I do not expect you to memorize them, but I do expect you to remember that they are part of Math Boot Camp and know to look back to them as you may need. The main rules that we're going to focus on are the 3 on the top and then the next 3. A lot of times we will have to multiply things that have exponents, and instead of having a long calculation, we will actually just add the exponents. To help this make a little bit more sense, let's look at some examples. Alright, let's start with example A. Example A is an addition problem. We have 4.53 times 10 to the 5th plus 2.2 times 10 to the 6th. When adding exponents, it's a lot like adding fractions. We have to have the end part be the same. Just like in a fraction, the denominator has to be the same in order for us to be able to add them. If I look at the 5 and the 6, there's one number difference, which means I can move either decimal place one space. I can move the 4 to the left, or I can move the 2.2 to the right. It will be easier in this example to move 4.4 or 4.5 to the left so that I don't end up having to move the decimal twice, because I would have to move it again at the end. So I'm going to rewrite this problem with the new decimal placing. That gives me 0.453 times 10 to the 6th plus 2.2 times 10 to the 6th. When I add exponents, they stay the same, just like adding the denominator of a fraction. So at the end, it's still going to be times 10 to the 6th. And then we know with addition, we start at the right and move to the left. So 3 plus 0 is 3, 5 plus 0 is 5, 4 plus 2 is 6, include our decimal, and then the 2. So the answer to this problem is 2.653 times 10 to the 6th. Moving on to example B. This is an example of a subtraction problem. It's going to work very similar to the addition problem. The first thing we have to do is look at our exponents. The first number doesn't have any. The bottom one has a 3. Same as the last problem, I can either move this decimal 3 places to the right, or I may move this decimal 3 places to the left. Because we're working with scientific notation, for this example, I want you to move the top decimal to the left. So if we rewrite this problem, we get 1.913 times 10 to the 3rd minus 4.6 times 10 to the third. Again, with the exponents in scientific notation, we're going to leave that alone. It's going to still be times 10 to the third. And then we subtract as we normally would, and that gives us a negative 2.687. So our overall answer is negative 2.687 times 10 to the third. Next is example C. Example C says 3.95 times 10 squared divided by 1.5 times 10 to the 6th. We're going to work this problem in two parts. We can do it either way. We can work with the number in front first, or we can work with the exponents first. We'll get the same answer. So let's do the number in front first. Okay. If I take 3.95 and divide by 1.5, I get 2.63. Next, we're going to work with the exponents. In order to divide exponents, I'm going to take the number that is the exponent and I'm going to subtract them. So I get 2 minus 6 equals negative 4. So if I write this all out as the full problem, I have 2.63 times 10 to the negative 4th. Alright, let's move on to our last example in working with exponents, a multiplication problem. Just like with the division problem, we're going to work with it in two pieces. The number before the scientific notation, and then the scientific notation itself. Okay. With the numbers before, we have 3.5 times 6.45, which equals 22.575. Next, working with the exponents, I have a 2 and a 10. And since these are being multiplied, I'm really going to add the exponents. So 10 plus 2 equals 12. Okay. If I were to rewrite this, I would have 22.575 times 10 to the 12th. This is not proper scientific notation because I have two numbers in front of the decimal. So we have to adjust it so that it is. I am going to move the decimal one place to the left, which means I'm going to add 1 to this 12. And that gives me 2.2575 times 10 to the 13th as the most correct answer in scientific notation. The next topic in Math Boot Camp is accuracy and precision. Accuracy is defined as how close a measurement is to the correct answer, how close the arrows hit the bullseye. And precision is how close measurements are to other measurements, so how well is our grouping of arrows. It is important to take your time so that measurements can be both accurate and precise during laboratory experiments. Let's look at some examples of accurate and precise. We're going to look at them both in picture form and as a list of numbers. If we look at accurate, there's one number that hit the bullseye. And then with this list of numbers, we have 1, 5, 10, and 2. And if the correct answer is 5, this would be accurate because only one of the numbers was correct. They're close to the right answer, but not close to each other. Next, let's look at precise. If we look at the diagram on the bullseye, all the arrows have landed close to each other, but they're not at the bullseye. So they're precise, but they're not accurate. Same goes for the numbers. If we have 1.2, 1.1, 1.2, and 1.3, but the correct answer is 1.8. The measurements we took are near each other, but they are not near the correct answer. measurements can be neither accurate or precise if none of them are the correct answer and none of them are near each other. If we were to look at numbers, we would have something such as 10, 15, 20, and 3, but a correct answer of 8. And then measurements can be both accurate and precise. Ideally, this is what we'd like. We want the best answer and the most correct answer possible. So if we were to look at actual numbers, we would have 0.52, 0.52, 0.51, and 0.53, hoping for a correct value of 0.52. It's okay to have numbers that are slightly off, depending on what the decimal place is and what the rest of the numbers are. The next topic we're going to move on to is significant figures. Significant figures are important because they tell us how certain the experimenter is in their measurements, or how precise they were. Our calculations at the end cannot be more precise than the measurements we took. Calculators, however, do not keep track of significant figures. We should always do all the calculations, then round at the end because instead of rounding at each step. If we round at each step, we may end up with an answer of 100, because that's what we get with the significant figures. But if we were to build a bridge only 100 meters long, when we really need to cover a hole that's 125, significant figures don't work to the best of our advantage. There are just a few rules for determining the number of significant figures in a value. All non-zero digits are significant. So if it's 1, 2, 3, 4, 5, 6, 7, 8, or 9, it's an important number. Zeros that are between any other non-zero number are significant. However, zeros in front of other non-zero digits are not significant under any circumstances. So next we have to concern ourselves with zeros that come after the end of the rest of the non-zero numbers. These numbers are only significant if there is a decimal place present. Let's go through some examples of determining the number of significant figures. First, let's look at the number 1,000. In this example, there is only one significant figure. These 3 zeros come after the 1, and there's not a decimal. So they are not significant. So for our reasoning, we're going to write zeros are after and no decimal. So next, let's look at the number 100, or 100.0. Because we have this decimal right here, that makes all of these numbers significant. So this number has 4 significant zeros. Okay, and our reasoning is simply going to be because there's a decimal and after. Okay. The same is true for the next number, 57.00. Because these numbers are after, and because there's a decimal, there is 4 significant numbers. This is like saying that you have exactly $57 in your wallet right now. So our reasoning, again, is going to be decimal and after. The next number we have is 0.00058. All of these zeros come before a number that is not 0. Therefore, they cannot be significant. They're simply just placeholders. So we only have 2 significant figures, and our reasoning is zeros are before. The next number we have is 50.3. In this instance, the 0 that we have is in between 2 numbers that are not 0. So that 0 has to be important. That means we have 3 significant figures. And our reasoning is the zeros in the middle. Next, we have 61.657. None of these numbers are 0, so all of them are important. Therefore, we have 5 significant figures. And our reasoning is no zeros. Okay. And then our last example is the number 1,000 with a decimal at the end. In this example, we have 4 significant figures because the zeros are after and there's a decimal. So the only rule you really have to worry about that can get confusing is the one where the zeros come afterwards. If there is a decimal, then those zeros are significant. If there is not a decimal, then those zeros are not significant. Sometimes a number needs to be rounded so that it has the proper number of significant figures. Rounding rules have been the same since kindergarten when you first learned about them. If we have to round a number up, it is because the digit following the place that we're rounding to is a 5 or greater. And if we have 4 or less in that next decimal place, then we're going to leave the number as it stands, making sure that we don't just get rid of things, but instead put in zeros as placeholders. It's also sometimes necessary to do calculations involving significant figures. But remember, we'll do all of our calculations first and round at the end. If we add or subtract, we're going to round to the decimal place of the number with the fewest digits past the decimal. However, if we multiply or divide, we're going to round the answer so that it has the same number of significant figures as the value with the fewest significant figures. To help you see how this works, let's try some examples. In example A, we're going to practice adding with significant figures. So first, I'm going to do the mathematical operation as if there were no significant figure concerns. So I have 0, 4, 13, so I'll carry my 1, make sure I include my decimal. 15, again, carry the 1, and 4. So I have 45.340. Because I'm adding, I'm going to focus on the decimal place of the number with the fewest decimals. So that's just one digit past the decimal. So if I were to rewrite this number correctly with significant figures, I would have 45.3. In this example, we do not increase this number to a 4 because the digit in the next space is a 4. Anything 4 or lower, we leave it as it is. Again, let's look at example B. This time we have subtraction. Our problem says 9.80 minus 4.762. So, as before, I'm going to do the calculation as I normally would. 9.80 minus 4.762 is 5.038. Again, we need to look at the number that has the least digits after the decimal. And that's the first one. So we're just going to draw a line, cutting off everything after that. So the correct significant figure notation for this number is 5.04. Making sure we round it up because this number here, this last number, is an 8. Now let's look at an example of multiplication. The problem in this example says 3.9 times 6.05 times 420. Both 3.9 and 420 have two significant figures. When I originally multiplied these numbers, I got 9,909.9. I need to round this number so that it only has two significant figures, based on the 3.9 number. So, that means I'm going to round at the clear the beginning. The only two sig figures we're going to have are the first two nines. The next number is a 0. That means I don't round up. I simply put 0. So, it will be 9,900 as our correct significant figure value. The last part of Math Boot Camp for today is Example D, a division example with significant figures. Example D says 14.1 divided by 5. If we were to do that math, we would get 2.82. But we need to round this so that it has the correct number of significant figures. If we look at our two numbers involved, 14.1 has three significant figures, while 5 only has one. That means our answer can only have one significant figure, which means I should only look at the first number presented, which is 2. Now I also need to consider, however, the next number. In this case, it's an 8, so we need to round up. So our correct answer, considering significant figures, is 3. That's all for today. Let's do a worksheet for you to practice, and we'll continue with Math Boot Camp tomorrow.